Yeah, this is me, and this is my title on iron trap hardware scaling and its future. Actually, on this talk, I will try to. This is the table of contents. Basically, I will talk about how the core hardware and trap starts. So my talk will start with hyperfine qubit splitting. Basically, this is, there are some energy levels actually. So these energy levels are okay. There are energy levels. So energy levels are splitted with magnetic field or electric field actually. So in this example, I have shown a hydrogen that has one proton and one electron, and every proton has spin up and spin down. So there are four splitting combination. For proton spin up, electron spin up, proton spin up, electron spin down, something like this actually. So this is known as hyperfine qubit structure. So the reason is why this is important. Basically, in typical energy band gap, there is these types of equation equal to h cut uh, multiplied by frequency actually. But we want in ion trap very narrow bandwidth. This is a problem for this kind of optical structure, and for this kind of electron we want a two electron stay in for a very long time. This is not possible for this kind of typical optical structure. For this reason we want actually hyperfine qubit structure. So some atoms show this kind of property. Basically, those atoms have outer shell electron 2 actually, and these are these are alkalite earth metals actually, materials actually, and these are some commonly people used by uh, yttrium actually. So typically in ion q, this is a chip for ion q, and these are, you see this, all of these are ion actually. So if I want to control this thing, so my laser bandwidth should be very narrow. And one of the very important things of using yttrium is that it has lighter mass actually. The mass is very low, so I can control them actually. And basically this is quite very easy to control actually. But typically the thing is that the ions are not rest in rest position. They start moving and like a spring from left and right, something like this. And there is a harmonic oscillation, something like this. Whole things moves around, something like this. So ions are restless actually, so I have to cool down these ions actually. So one of the things is that how ions can be trapped actually. Basically, to trap ion in an energy gap, there is a Earnshaw theorem that shows that static electric field cannot trap ions actually. So I need three-dimensional electric field, and this three-dimensional AC electric field creates a saddle point actually. You see something like this. And if I don't apply AC electric field, this ion will either slide down actually, something like this actually. But this three-dimensional AC electric field makes it a traps in a point actually. So I need a Doppler cooling actually. So for Doppler cooling, the thing I do, uh, atoms is moving to opposite directions and I imply photon to opposite direction. So applying laser to atoms makes transitions, creates transitions. And basically the things happens, photon, applying photon on a atoms, this absorbs the photon, and on the other hand it also lose its momentum actually, kinetic energy. So the losing of kinetic energy creates a separate wavelengths. So I am applying photon and this is losing its energy, so that's why it is getting rest actually. So this is the reason I am saying Doppler cooling. And the thing is something like this, opposite things happen this kind of Doppler cooling actually. Yeah. And to compute the things, I have to create ground state. One of the things to create a ground state, that if I one atom ions is in spin up, the others is spin down. So if I make a pair something like this, so all of these atoms ions are in ground state. And there is a famous Sirac-Zoller CNOT gate to make a computational CNOT gates, and there is a mentioned paper I mentioned it. And there are some big vendors like IonQ, and at this moment they are in 22 qubits, and they have a roadmap. And here is Honeywell, and they are at the end, if I'm not wrong, they cracked the architecture, and there are some others company are working on this ion trap technology. Actually, yeah, that's basic of ion trap hardware actually.
Thank you. Thank you for the talk. If there's any questions, please ask in chat or raise your hand. I have a general question. What is the advantages of trapped ion quantum computing compared to other types of quantum computing?
Yeah, one of the great advantages is that the typically in superconducting qubits, there is some decoherence something like this, and it is for the most updated is milliseconds actually. But if I trap a ion, like in this ion trap actually, in saddle point actually, the ion stay for a very long time. Even it can be stay for a 1 day, 2 day, or even a week actually. So the more longer a ion can stay and the qubit stay, the more I can compute. So basically this is one of the great advantages actually. One question: how does it compare to superconducting qubit noise wise? Basically, yeah, in noise wise, at this moment, I can say that ion q is trying to say that they approached a different types of algorithm, like say, for calculating noise I need a error correcting qubits actually. So typically ion traps or ions are very pristine actually. They have a very good fidelity, if I'm not wrong, 99.97% actually. So in this case almost they are very same at this level actually. So but they are struggling actually, in the sense because 99.97 still is very uh, quite I should say 99.97 fidelity is not much up to the mark, because I need a very good amount of qubit to make a error correction course actually. So in that sense, yeah, this is also struggling, but this is good. Ions are pristine actually. The way I'm creating ions, they are very much pristine actually. Yeah. I think if you have any further more question, you can contact me in Twitter or in Discord, whatever. Yeah, and yeah, that's it.
We have time for more questions. I think another question. So there's one more question in chat. Would you like to answer?
Any drawbacks you could share when considering trap ions architecture as scalable quantum computing? Okay, for a scalable quantum computing, let's say I have 22 ions, and that means I have 22 qubits. So this is the only thing you can say. So now let's say I want to create a 44 qubits, because if there is 22, so I need if I have another 22 qubit chips, then how I can make it connection with these things actually. So if I'm the question is drawbacks actually. So one of the drawbacks is that to make connection, these, let's say I have these ions at the right left side actually, and I have another chip, so there should be similar kind of things, and there will be right side ion. So let's say I want to make connections actually. So in this, when I want to create a virtual connection, so those may not be somehow very that much entangled fidelity actually. So entanglement connection may not be very good actually when I'm making connections with two different chips to create a scalable quantum computer actually. So yeah, this is one of the drawback actually for scaling ion trap chip actually. Yeah, because all of the vendors are almost following these types of technology actually. So they have to scaling up, and they have to make connection this qubit with another chip's qubit. So entangled property somehow gets lost, quite lost actually. Yeah.